So thank you, Robert, for the nice introduction. I also want to introduce myself a little bit. My name is Kerschbaummayr. I'm a research scientist in the laser ultrasound group at the Research Center for Non-Destructive Testing. And as mentioned before, I want to give you an overview today about in situ laser ultrasound measurements of austenitic grain growth in plain carbon steel. So let's have a look at the agenda today. I think there are some people in here who are not very familiar with the laser ultrasound principle. So I will give an overview about laser ultrasound principle. Then I will show you some typical applications of laser ultrasound. Then I will introduce you to the adapted thermal simulator from our labs, the accessible acoustic parameters and the interpretation. And after that, I want to give you an insight about the measurements of austenitic grain growth. And at last, I want to sum up everything and some acknowledgements. So let's start with the laser ultrasound principle. At the non-destructive testing method, a laser ultrasound, the ultrasound wave is generated contactless by a short laser pulse, which is fired on the sample surface. You can see a thermal expansion of the surface, which provides the ultrasound wave to travel through the material. And with a second laser, we can detect the surface displacement and we can detect the surface displacement of the ultrasound wave, and we get those typical laser ultrasound signals. So what is the benefit of laser ultrasound? It is completely contactless. We don't need a coupling media like for conventional ultrasound testing. With the short laser pulses, we have a high bandwidth, and the method is also suitable for very harsh environments like measuring on hot or on glowing surfaces. So we have different waves which are propagating in the material. So for example, for a bulk geometry, we have the bulk waves, which travel longitudinally or transversal through the material. And we have also some surface acoustic waves, the Rayleigh waves, which travel along the sample surface. When we are measuring a plate geometry, we have some guided waves in the plates, like the lamp waves, which occurs in resonant modes. There are the zero group velocity modes, and also thickness modes, like the longitudinal and shear modes. So what are some typical applications for laser ultrasound? Laser ultrasound can be used to detect inclusions, cracks or pores in steel and aluminum. It can be used for determination of the hardness penetration depth and also for the quality inspection of welded joints. Can also be used for investigations on carbon fiber reinforced polymer parts, like to detect delaminations in the material, and also characterization of electronic components and filters, or the analysis of elastic parameters in the nanoscale. So let's jump into the next topic, the adapted thermal simulator. In our lab, we have a thermal simulator, a dilatometer from the company InSitu, where we adapted our laser ultrasound measurement system for the in situ measurements. Here you can see the dilatometer on the left side, and on the right side, there's the excitation laser from the company Quantel with a maximum pulse energy of 850 millijoules. And for detection, we use an industrial Techno system. So here is the view a little bit more zoomed in. There's the vacuum chamber of the dilatometer, where we have integrated special windows where we can guide the laser beams directly onto the sample. We have an inductive heating coil for heating up the samples. The sample is placed in between there, as you can see here. And there's also a picture of a hot sample with a format of 6 × 6 × 10 millimeters. So what are the accessible acoustic parameters and their interpretation? I want to give you an overview now. The first parameter we can measure is the ultrasound velocity, which is a direct measurement of the time of flight, the delta t, between two ultrasound echoes. So the ultrasound wave is traveling through the material and we get the first echo here. And the second echo, the ultrasound wave is traveling 3 times through the material. So we can directly calculate the velocity when we are knowing the thickness of the material. So what can we show with ultrasound velocity measurement? First is the phase transition. On this slide, you can see an in-situ measurement of the phase transition based on the length change in the upper graph and also the change in the speed of sound in the lower graph. So in the red circles, there's the phase transition in the heating, and in the blue circles, the phase transition during cooling of the sample. So with this information, we can determine the phase fraction from ferrite to austenite or austenite to martensite with a so-called law of mixtures during the cooling process. So on the right side, we show that the length change and the change in speed of sound are nearly the same, and they fit very well in the cooling of the samples. So we can also measure the recrystallization with laser ultrasound. On this slide, you can see the measurement of a recrystallization in ultra-low carbon steel during isothermal holding at different temperatures from 680 degrees to 720 degrees. We have some micrographs here. On the left one is the initial state where the texture is in rolling direction. And on the right side, there's a micrograph where the recrystallization is completely done. Yeah. On the left, we can see the change in the ultrasound velocity. As you can see here, the more high the temperature, desto faster the approach, the recrystallization is done. So the second acoustic parameter which we are interested in and can measure with laser ultrasound is the frequency-dependent ultrasound attenuation. We can measure this attenuation by putting the amplitude spectra of 2 echoes in considering the sample thickness d with this formula. So we can see here the first echo, we make a fast Fourier transformation to get the amplitude spectra. And for the second echo, the same. And by putting these into relation, we get the frequency-dependent attenuation. And this parameter is used for the grain group measurements, where I won't jump into more detail now. So let's start with the in-situ laser ultrasound measurements for the austenitic grain growth. At first, a little bit about motivation. The austenitic grain size is an important parameter for the steel production industry. Why? Because it influences the final microstructure and the properties of the material. For example, the hardness or the ductility. So for conventional grain growth determination, samples have to be prepared for each desired temperature. They have to be heat treated. Then they have to be rapid cooled down. It's the so-called quenching to freeze the current microstructure. Afterwards, the samples have to be polished and etched. And after that, the samples have to be analyzed under the microscope to analyze the microstructure. And afterwards, the micrographs have to be evaluated of mean grain size, for example, with the line cutting method. And this is a very time-consuming process. So there are in-situ methods desired to capture the microstructure changes in situ, and laser ultrasound is a suitable technology to help to accelerate those microstructure studies. So we had an external partner which provided us some samples from the plain carbon steel and also offers us a temperature program where we get an expected average grain diameter from 5 to 120 micrometers. So there are 10 samples which are heat treated in the dilatometer and then are cooled down at different interrupt times and interrupt temperatures. And afterwards they were analyzed about average grain diameter to get a good overview what's happening in the material. So we have afterwards used 5 new samples for the model calibration with laser ultrasound. Yeah. So at first I want to give you some basic information in the physical principle. Ultrasound waves are influenced by different physical phenomena. There's the attenuation contribution due to internal friction, which is very weak frequency dependent. Then there's also the attenuation contribution to grain scattering, which we are interested in. And there's also an attenuation contribution due to diffraction. So to eliminate this diffraction-induced attenuation, we are putting the actual measured amplitude spectra of the first ultrasound echo in relation to that of the first echo from a reference measurement. The reference measurement is at 830 degrees, where the austenitization starts. So we can eliminate the diffraction contribution, and as told before, the internal friction is weak frequency dependent, so we can take it as a constant afterwards. So the attenuation scattering coefficient may then be modeled with a frequency power law, where A accounts for the internal friction, and the second term B accounts for grain boundary scattering induced attenuation. D is the relative change of the grain size, and the exponent n depends on the scattering regime and the grain size distribution. So n is determined by the fraction of the wavelength and average grain size, and there are some different scattering regimes where n can take values from 0 to 4. There's n takes 4 in the low frequency Rayleigh scattering regime, n is 2 in the stochastic scattering regime, and n is 0 in the geometric scattering regime. So in previous publications, they often use a value of 3 because it's a good intermediate value because between 4 and 2. But in our approach, we are varying the parameter n in different regions. So the B parameter in this equation consists of a material dependent parameter C and also the relative changes of grain size. So that means that B parameter is directly related to the mean grain size. So what are we doing now? We make a model calibration, and to obtain the parameter C and N, a two-step calibration is applied. So the exponent N is varied in a physically meaningful region between 2 and 4. And the B parameter values is determined from fitting the power law into the attenuation spectra of the different supporting points. As you can see in this figure, the attenuation increases with the occurring grain growth, which fits very well. So the scattering coefficient C results in the slope of the linear regression line between the B parameter values and the relative changes in mean grain size from the micrographs. So we have here for the optimized model an exponent n of 2.34, and this C parameter is used for the final model then. So with the grain size can then be determined for every recorded loss attenuation. On this picture you can see the comparison of the estimated laser ultrasound grain size with the InSitu micrographs from the analyzers. And then we calculate the root mean square error of laser ultrasound grain size and InSitu grain size. So the calibration process is repeated then for different values of the exponent n. On this picture, you can see the least error at exponent value of 2.4 for sample numbers 3. So we did this on 5 different samples and make an average of that. And this averaged value, 2.34, we took for the final attenuation model. So let's jump into the results and calibration model application. On this slide, you can see the model application, where we used the final attenuation model for an in situ measurement. And the crosses in the picture here are the micrographs to show that the results are very good. So we had also a second sample measured, where a slight deviation is in the first 200 seconds. But all in all, it seems to be very good. Yes, to sum everything up, laser ultrasound has great advantages in specific applications. The dilatometer thermal simulator is equipped with a laser ultrasound system. We can measure the phase transitions and recrystallization derived from ultrasound velocity. Then Austenitic rainbow derived from ultrasound attenuation for developing a robust and optimized attenuation model. We verificate that on plain carbon steel. And currently we have some in situ studies in progress on other materials like Inconel 718, titanium and aluminum. And another one is we have sheet metal investigations with plate wave methods for additional material parameters. So at last, I want to thank all my colleagues from the laser ultrasonic group and also the physical and computational acoustic group at the RECENDT, and of course all the external partners. And I want to also thank you all for listening today and for your attention. So on the last slide, I have added the contact data from me and my colleagues. If you have some questions or want to get in touch with us after this talk. So thank you very much.
Thank you so much, Christian Kerschbaummayr, for your talk.